Hello there, welcome back to another video. Today, we're going to be talking about U-substitution. Now, U-substitution is the most important rule in all of integration. And it's also the most fun one out of all of them. And today, I'm going to be showing you how to use U-substitution effectively. And also, I'm going to be showing you a trick that can save you minutes on actual U-substitution questions. So, let's get into it. First off, we start again with derivatives because you see U-substitution is going to relate to this derivative question. So let's start with this, the derivative of sine x squared. So since there's an inner function being x squared and there's an outer function being sine, it means that we'll have to use chain rule. And in using chain rule, we have to take first the derivative of the outer function, so sine prime x squared times and then x squared prime, because we take the derivative of the inner function. So then we get the derivative of sine is cosine, so we get cosine x squared times 2x, because that's the derivative of x squared. So we end up getting 2x cosine x squared. Okay, that wasn't too bad. That was just a typical derivative question. And would you look at that? Now it's asking us to find the integral of 2x cosine x squared. Now this is where things get a little bit more fun, but I'm going to show you that this is actually not too difficult at all. And before we start with this question, we want to select what we want to substitute as u. Now the thing is, with u, what we're going to do is we're going to take the derivative of u. Du over dx is equal to something. So u is equal to question mark. We'll just say that for now. And du over dx is equal to question mark. And then what we're supposed to do here is we're supposed to isolate dx. So we get dx is equal to du over question mark, right? And then we can substitute this du over question mark into dx, right? So we need to decide a question mark that can sort of cancel out with any of these terms. So as you notice, if we choose cosine x squared as our u, that won't work, because that'll give us sine x, because if we take the derivative of cosine, that'll give us sine, but that won't work. Then let's try x squared. Well, if we take the derivative of x squared, we get 2x, and then, oh, you see there's a 2x there, which can cancel out. So let's actually try that. So let's say u is x squared. So that means du over dx is 2x. And then we can rearrange this, so we can get dx on the top and 2x on the bottom. So you get dx isolated is equal to du over 2x. Okay, great. So we know this is u, and then we know this is du over 2x. So let's substitute that in. So after substitution, I'll put this in blue. After substitution, we get integral of 2x cosine u du over 2x. But as you can see, I can just simplify this now, right? Because I got 2x here and I got 2x here, which means I can cancel and cancel, which means all I'm left with, and this is the magic of choosing the right u. It allows us to cancel the values inside the actual function. So this then leaves us with cosine u du. Now, the fact that it's du and it's u doesn't make a difference. We still follow the same procedure, taking the integral as if it were x. So using the same procedure, the integral of cosine u will be sine u. And since this is an indefinite integral, we talked about this last time, we do plus c. And then our last step can be substituting in back u. So we get sine, and then we said u is x squared, so we get sine x squared plus c. And would you look at that? That's exactly what we just took the derivative of in question 1. So as you can see, U-substitution is actually the opposite of chain rule. So if you have a function inside a function, most of the time you would use U-substitution, because U-substitution allows us to simplify the function so we can calculate it. So that's a general example. Now let's do a different problem now. Integral of x divided by x squared plus 1 dx. Okay, again, one really important tip is that if you have a fraction, you should probably take the derivative of the denominator, because once you cancel out the denominator, it helps cancelling the numerator. And I'll show you what that means. We can also see that if we take the derivative of x squared here, it'll simplify to 2x, and then we can cancel that 2x with this x. And then this 1 can just get cancelled out if we take its derivative. So then we can set u as x squared plus 1. So then we get du over dx is equal to 2x, and dx then is equal to du over 2x. So then we can substitute. So let's put another gap there. So after substitution, we get integral of x over u times du over 2x. Now I can cancel this x and I can cancel this x. And that leaves me with integral of 1/2 times 1 over u du. And what I can also do is I can bring this 1/2 outside, because in an integral, we don't care about the coefficient. 1 over 2 is just a coefficient, and we can factor it out. So if we factor that out, we get this, 1/2 integral of 1 over u du. Now, just for the final step, we need to take the integral of 1 over u du. We treat it just as x. It's the same thing. It behaves the same way. But the thing is, remember, 1 over u or 1 over x is an exception. So we can't use power rule here. This, we have to know this is the exception. So we have to say it's 1 over 2 ln u plus c, since it's an indefinite integral. And then all we got to do for our final step is substitute back in u. So you get 1/2 ln x squared plus 1 plus c. And that right there is our final answer. Okay, let's move on to the next question. The next question is quite a simple one. It's sine 5x. But this instead is a definite integral. So we'll have to do some sort of change in the bounds, but we'll get into that once we get to it. So first we start off with picking our u. We can either pick sine as our u, or we can pick 5x as our u. And the general rule is that we pick the inner function as our u, which means we pick 5x as our u. 5x is equal to u, which means our du over dx will be 5. And then we can isolate dx, so we get dx is equal to du over 5. So we know this is our u, we know this is du over 5. So now we can sort of plug these in. So we get the integral of, we'll worry about the upper bound and lower bound at the end. But first we can say that this is sine u du over 5. And then we can bring the 5 outside, so we get 1 over 5 integral of sine u du. Now what I should do here is I should plug in my error bounds, since right now these error bounds match with dx, but I've changed my entire integral to match u, which means I need to change my bounds too. So in this case, it means my upper bound then, u, is equal to 5 times pi, which is equal to 5 pi. And then my lower bound, I'll call it L, is equal to 5 times 0, which is equal to 0. Which means now I take my integral becomes 1 over 5 integral of from 0 to 5 pi of sine u du. Now the integral of sine u is negative cosine u. Be careful, this is a very common mistake to make. It's the derivative of sine u is cosine u, but the integral of sine u is negative cosine u. So in this case, we'll get 1 over 5, and then we don't put c, we put the bracket, so we get negative cosine u, and then close bracket from 0 to 5 pi. And now we can plug in our values, so we get 1 over 5 on the outside. Remember, 1 over 5 stays outside. Then we put another bracket, negative cosine 5 pi, minus negative, and then we remember to put the brackets, they're really important, cosine 0, and then we close the bracket. Then finally, we can now calculate these. So cosine 5 pi is the same as cosine pi, and cosine pi is just 0. So we can say this is 0, and all we're left with then is 1 over 5 cosine 0, and cosine 0 is just 1, so we get 1 over 5 times 1, which means our final answer is 1 over 5. And just like that, we have solved this problem. So it seems really long and complicated, but the steps themselves are easy and quite self-explanatory. And let's apply that one more time to the last question. Question 5. The integral of 1 over 3x minus 1 dx from 0 to 2. Now let me teach you one trick real quick. That'll make solving this integral so much faster. And it looks something like this. Whenever we have any sort of inner function that is a linear function, so it's 3x minus 1, we can put that in y is equal to mx plus b, and it'll follow that form. Whenever we have a linear inner function, what we can do is we can take the coefficient of x and we put it 1 over that number outside our integral. Then we take the integral of 1 over u du, and that's it. And I'm getting this 1 over u by plugging in u into this. So I already know this is going to be my u. And what I've just done here is I've skipped a step here. And this works always whenever you have only a linear inner function. So this is a linear inner function. So, okay, great. Well, I'm almost done, right? Now I just have to change my bounds. So instead of 2 to 0, I need to first plug in for 2. So u is equal to 3 times 2 minus 1, which is equal to 5. And then for my lower bound, it's u is equal to 3 times 0 minus 1, which is equal to negative 1. So then my bounds change from 0 and 2 to negative 1 and 5. And then all I have to do after that is just take the integral of 1 over u. So it's 1 over 3 ln u from negative 1 to 5. Now, because I've changed my bounds, I don't need to worry about this u. I don't need to change it back into x, which means now all I have to say is 1 over 3, then big bracket, ln 5 minus ln negative 1, and we put the big bracket outside. Now, you can't take a natural log of any negative number, so that does not exist, which leaves us with the final answer, 1 over 3 ln 5. And that right there is our final answer. So that's it for U-substitution. I hope this has helped in making you understand the basics of U-substitution, why we do it, and a couple of tricks on how to make it faster. And yeah, I wish you the best of luck in your U-substitution learning journey. And next video, I'm going to be talking about integration by parts. So I'll see you then. Bye-bye.